One more time, hello everyone. It's my pleasure to see you all again. And today we are going to explore further the idea of Greybox fuzzing, but now we are going to combine it with the concept of grammars that we have already seen, namely bringing the best together of Greybox fuzzing, meaning that we operate with feedback from the program at hand, and also grammars, namely exploiting our knowledge about the input structure. And we're going to look into three different techniques today, all of which are combined in one chapter, and actually all of which are among the most powerful fuzzing techniques invented. Last but not least, because they have indeed discovered thousands and thousands of bugs. If you are looking at this from your web browser, for instance, your web browser essentially works as it should, not also because precisely the techniques that we're looking into this chapter actually have detected thousands of bugs that have been fixed in this very web browser. Okay, so conceptually, all these techniques are rather simple. However, there's a bit of implementation associated with them. So, let me just share my screen here. Let's see. Here we go into Greybox fuzzing with grammars. The first technique we're going to look into is called dictionary-based fuzzing. The idea is that we are having that we want to mutate inputs, but when we mutate inputs, our chances of generating specific inputs that are of value, for instance, keywords or other fixed strings, are rather small. Well, you can do the math. If you have a keyword with, say, 3 letters, generating these 3 letters by chance and then achieving new coverage is fairly slim. So we are introducing the concept of a dictionary. And a dictionary simply means that we do have a collection of fixed strings which we also can use as mutations. So before we had mutations such as inserting random characters or deleting characters or flipping characters. Now we're also having another mutation, namely introducing a word from a dictionary. Here's an example. This is a simple HTML text. You already see that one. And we can now take an element from the dictionary and insert it. And if our dictionary, say, comprises lots and lots of small HTML fragments, yes, we're going to get a much, much higher coverage in our code later on. Hey, maybe we should have some log4j fragment in there, and then we could happily test whether our system in question is vulnerable to the log4shell attack. So that's already all there is. Very simple concept. Have a dictionary with plenty of predefined words, and this will make your fuzzing immediately way more efficient, because then your inputs, in particular the newly inserted inputs, will not only consist of random characters, but actually also of random sequences of keywords. So that's fairly simple, and that's already the very first concept we're looking into. And the way we are implementing this is pretty simple. We're introducing a new mutator class. This is called the dict mutator, and the constructor of the dict mutator takes a sequence of possible keywords, a dictionary that is, and from there on it will use its mutation capabilities to add another mutation method, namely to insert a character from a dictionary. I'm going to skip the implementation here because, well, this is just very straightforward, as you can imagine. So this is the first method, and this is a method that is actually implemented in the AFL fuzzer. So in AFL, you can supply a dictionary, and obviously, the better your dictionary is, the higher your chances of actually getting good results with your fuzzer. So that's already the first thing. And of course it will be guided by coverage and everything. So very simple concept gets you pretty far already. That's our first technique. Our second technique that we're looking into is fuzzing with input fragments. So rather than having a dictionary of possible tokens, possible small parts, we are using an anti-grammar to parse inputs, and we are having a big collection of inputs that we are using and parsing to obtain plenty of input fragments. All this, when we are parsing these, gives us lots and lots of derivation trees, such as this one. So this is a derivation tree that we get from parsing the HTML text that we have seen earlier. And if we do have such a derivation tree, we can do plenty of manipulations with it. For instance, we can just go and swap two arbitrary parts of that tree, assuming they would be compatible with each other. Or if we do have a large collection, then we can swap across a large collection of parts. And this also allows us to reuse plenty of fragments from existing files and happily recombine them. Not only can we recombine things, but we can also go and generate new parts. And this works by taking a subtree and happily deleting it. Now we have a missing subtree in here. But however, we can now go and just generate a new part in here. So now we have generated this new part from the rules of our grammar. We get some meta name attribute whatsoever, or we can generate arbitrary new parts. And this combination of being able to reuse parts of existing inputs and also generate new parts actually has proven to be enormously effective. And when I say enormously effective, this is something we implement in a fuzzer called the lang fuzzer. And lang fuzzer is a reference to a tool, to a fuzzer named lang fuzz, without the ER, that was published some 10 years ago at Usenix. I was one of the co-authors of that paper, so I have particularly fond memories for that. And lang fuzzer actually exactly implements this technique of taking existing inputs and recombining them at will and generating new ones. And it does so with a grammar that can be passed as a parameter. It is almost an exclusive use for JavaScript. And what this means is it generates arbitrary parts from JavaScript programs, puts them together in U, and throws these at a JavaScript interpreter. And it does not take arbitrary JavaScript inputs. Well, actually it takes arbitrary JavaScript inputs, but it's particularly effective when the set of JavaScript inputs it learns from has created bugs before. So what my student Christian Holler did was he collected plenty of JavaScript samples from security vulnerability reports and likewise, all of which had been fixed, mind you, and happily recombined all these. And as he was recombining all these, he would go and create new mutations all across the board. And this way, he would generate plenty of new JavaScript inputs that all contained fragments from elements that had caused bugs in the past before. So this was his tool, langfuzz, and he let it run. And within 4 weeks of running his tool, he had netted $50,000 in bug bounties. $50,000 in bug bounties. Now that's a great thing for a master's thesis. And since then he has been continuing to run his tool, and Langfuzz so far has discovered more than 2,600 bugs in the JavaScript interpreters of Chrome, of Edge, and of course of Firefox. And sometimes I get asked, so if he got $50,000 in bug bounties in the first 4 weeks, how much money did he make in the next 4 weeks? I cannot tell you that, because after 4 weeks, the folks from Mozilla, the makers of Firefox, came along and said, okay, rather than paying you bug bounties, we would rather like to hire you right away as a security consultant, and he happily accepted. And since then, he has been happily working as a senior security engineer for Mozilla, and one of his works actually is still running Langfuzz all day long, 24/7, on a big cluster of servers, and all this is there fuzzing happily, just to make sure that the JavaScript interpreter of Firefox works as advertised. Similar things are in place for Chrome. Similar things are in place for Microsoft Edge. And at some point, Christian reported he was in talks with Apple too, but Apple seems to have decided to do this themselves. So everybody is fuzzing JavaScript interpreters like crazy using this very technique. So any browser you're looking through right now is being fuzzed all day long very effectively. So that's our second technique already. This is our second technique, and our second technique, the langfuzzer, is also implemented. Well, there is a specific langfuzzer class in here, and the key idea here is to have a special mutator, namely the fragment mutator, in which you can add fragments as derivation trees, as parse derivation trees to a pool. There's a special method for that, add to fragment pool. And then the fragment mutator will happily pick fragments from a derivation tree and either delete them or swap them or put in new places from the pool. So plenty of opportunities here just as well. And this, ladies and gentlemen, was our second technique. Our third and last technique also uses grammars, but in a slightly different way. And that's a bit more complicated, and I'm going to explain this again using a couple of diagrams here. Our third technique is called region-based mutation. And region-based mutation actually is pretty similar to what you have seen with the langfuzzer before, except that it works by only parsing things, so without generating new ones. And the way this works is as follows. Again, we're having a string, and we are still having the same HTML part here as it was from beginning to end. And now, again, we're using an existing parser to parse this thing, and this again gets us a nice derivation tree. And now we are not working on this derivation tree, but rather we are using the boundaries of the individual parts as they are parsed by the derivation tree as so-called regions, indicating regions in the input string that we can go and actually replace and swap again. And this has the advantage of not being so tied to the abilities of a derivation tree. It is more robust. It also brings the potential disadvantage of creating inputs that are syntactically not fully correct. But on the other hand, if it's not syntactically fully correct, who cares? We are doing fuzzing. So actually, syntactically invalid inputs can actually also cause bugs. So how does this work? So we're identifying individual regions in here. Here's one region, as we can already see. This all is equivalent to one subtree in the derivation tree. Here's another region, which is also induced by parts of the derivation tree. And now we're having these two regions, and well, we can swap them and place them back again into our input. And now we are also having mutations that actually apply sort of syntactically aware, syntax-aware changes to the input. However, by being based on region, they are more robust than the technique we previously had in lang-fuzzer. And this technique has been implemented in a fuzzer called AFL Smart. AFL Smart is a variant of AFL that takes so-called peach pits as language descriptions, and peach pits are syntax descriptions for fuzzers. And using these syntax descriptions, it is actually able to AFL Smart is actually able to very efficiently identify boundaries where it makes sense to cut away pieces and swap them, because the parser would tell AFL Smart where individual important chunks in the input begin and where they end. And this is all combined with the power of AFL itself. There's even a special schedule, a special power schedule that is tailored towards these boundaries. And all of this results in a very efficient fuzzing method, which is syntax aware. And this comes as an expansion of the fragment mutator. Now we have a region mutator. The region mutator picks a particular region in the input and mutates it. This is implemented again in the Greybox. This is implemented in a fuzzer called the Greybox grammar fuzzer, which implements this AFL Smart technique. And we also have a smart schedule which assigns energy to inputs depending on how valid they are, giving more power to inputs that are actually valid. And again, for all these three fuzzers, we do have examples, so you can start at the very beginning. There's a synopsis on how to use each of these. And of course, you can also go down here into the actual implementation and see how they work, including something that you cannot get in a printed book, animated diagrams in here. And this also comes with a couple of evaluations comparing the variance comparing the variance against each other. Here you can see, for instance, that for the dictionary-based fuzzer, you can see that if you do have a dictionary, you very immediately get a much higher coverage than with the fuzzer without a dictionary, which actually takes 2,000 inputs before it actually overtakes the fuzzer with a dictionary. This is actually something that we frequently see in fuzzing. If you have knowledge about syntax and about the constraints and everything, what you're going to see is a big boost in the very beginning, and this makes the fuzzer far more efficient. However, and that's interesting, in the long run, in the very long run, it is the pure random fuzzer that will eventually win, because in the very long run, the random fuzzer is guaranteed to cover all possible inputs. Well, very long can be hundreds or even millions or billions of years, but at some point it's going to cover everything. Okay, because at some point it will have enumerated all possible inputs, in particular, of course, if it's coverage guided. But if you have little time for testing, and who hasn't, then going for any of these syntax-aware approaches can go a long way. And you have the choice. You can either go with a dictionary, as with our dictionary-based fuzzing, or you can throw in a full-fledged grammar and include coverage guidance and have fun with that too. And this already brings me to the end of today's presentation. If you are interested in these techniques of Greybox fuzzing with grammars, there's also a new fuzzer that we're building over here at CISPA, which is called Format Fuzzer. And this is actually set to bring all the best of all these worlds together, namely to allow for generating inputs, for parsing inputs, for recombining inputs, and also with AFL guidance, all together in one single package. And I would love if you could take a look. Just enter Format Fuzzer into your favorite search engine, and it will happily get you towards our latest and greatest. So that's all for today. Thank you very much, and looking forward to see your next advances in fuzzing technology. Thank you.